uses it needs to have some basis for why that physical property is, why that constant looks the way that it does from the first principles of what it is actually describing. If we can't figure that out, then we're sort of stuck with either accepting this.
Like if Planck wants to ignore the material properties that give him his equation, in other words, the black chamber that does it, then he destroys the concept of temperature for all of humanity. But if he wants to acknowledge that he used an idealized situation, then all he does is have to modify Boltzmann's thingy, and then we just have like refractive index or something. We just have like material-specific distributions of temperature within a body. So, I just think that in order to save some of these broader concepts, whether it's force or temperature or something like that, we might have to rethink some of the constants of nature, essentially.
Yeah, that might be the case. Something I would emphasize, though, is that just because you don't have an explanation for why a given constant is the way that it is, doesn't invalidate the claims. When Hooke said, the stiffness is just K, like that really means something. But and it's limited. There might be more to the story, but in this context, that really, to a certain level of accuracy, that really captures the stiffness of the spring. It really does. And you want to find an explanation for it, but just because you don't have an explanation doesn't mean it's wrong. It's right. And yeah.
I think that what I would say is that it is right, but that you should be able to come up with an explanation for why certain materials have a specific K.
What if he'd made K stay constant? He was like, K is always the same. And then you're like, well, but then I calculate different X's. And he's like, well, that's just the effective X. That's not really the length. That's just the effective length.
But that would be madness, because
that's what they've done with temperature. That's all I'm saying.
Oh, I see.
Yeah.
Well, so, but I'll identify.
It is madness.
Okay, right. This is a reductio you're doing. So, why specifically is it madness? It's because you'd have to have a special set of ways of measuring distance that work for springs that's completely different from the way you'd measure distance in every other context.
Yeah. Well, that would be like Hooke.
You're not going to change that. You're going to change K.
Yeah, because Hooke did his experiment on this one spring, and the spring had a springiness to it, and he was like, "That's the same for all materials." And he's like, "Kind of right. Like there is a springiness. Like you know what I mean?"
Right?
But he like, of course, people had the wherewithal at the time to realize that they should probably change the prefactor, and not the distance shouldn't be labeled as some effective distance.
Well, he probably tried multiple springs.
He probably did. I'm sure this was easily avoided. It could have easily been avoided with the black body work as well, but it wasn't, because Planck wasn't an experimentalist, and he couldn't care less about that. He just wanted to take the ideal and extend it to all of reality, because why not? That'd be really nice.
He had his pet theory, and he was just advocating for it.
Yeah, and if the temperatures are incorrect, well, that's just the temperature of the rays. It's not really the temperature of the body anyways, so it doesn't really matter. It's the effective temperature. I don't know. I imagine that this kind of thing is cropping up all over the place. And if we're going to try to rescue our physical understanding of the major variables in our physical theories, we might have to think a bit more about the context under which those variables were interrogated, which usually means going back to the history books and studying these experiments and studying these miserable 300-page proofs and seeing like, how the hell does this go off the rails? Like, what the heck happened here? Which is kind of where we started at the beginning of all of this. Most people don't have the time for that. And I think that's a real tragedy of perhaps the program of education that, as a humanity, we've gotten behind. Because we're really good at being ready for the workforce, but we're not particularly great at innovating anymore.
At least not on the fundamental levels of science, because we stand atop an enormous skyscraper of achievement before us, that came before us. When we talk about Maxwell's equations, when we talk about general relativity, when we talk about all these things, it's the billionth floor of the skyscraper, and a bunch of the floors beneath us are just shrouded in clouds. We don't know how we built to this point. And so to understand the point we're at now, the work is going to have to be done. This historical work is going to have to be done to go back to the observations and the reasoning steps that supposedly proved this stuff to begin with. And what we're going to find is that some of it was never really proven. Oh, here's a concrete example that I think you guys wanted to talk about. We can move on if you want. But when I looked at the evidence that the electron is a particle, here's the evidence that I've seen so far. I might be missing some of it because I maybe need to study the history better, but here's my understanding. The evidence is that the first bit of evidence was during an electrolysis reaction, charges are passed around in discrete units per mole. And so that lent itself to a natural hypothesis that the atoms were passing around individual charged particles. Then later, Thomson shoots these particles across a beam and he finds that they have a certain mass per charge. Then Millikan finds the discrete unit of charge by levitating a bunch of oil droplets, and he finds that each of them have some certain unit of charge. And so this is starting to look very convincing. Yeah, the atoms are passing around these little particles, and each particle has a certain mass and a certain amount of charge. Totally reasonable hypothesis, might be true, but it doesn't prove it, especially in light of the fact that there's another kind of phenomena that could account for this, which is the passing around of a wave. So is that the atom absorbs and emits, it could be the fact that the electron is a wave, and these waves are absorbed and emitted in such a way that it will always have a certain amount of mass and it'll always have some certain amount of charge. And you can only have, and why is it that this wave can only be absorbed and emitted in certain ways? Because if you think about a musical instrument, that's the way it is. It can only vibrate at certain frequencies because of its structure. And so it can only accept or emit certain frequencies. And maybe that pans out in such a way as to produce discrete charge and discrete mass. And so this is an example where, it's proven it's a particle. But then you look back, are you sure it was proven? You have to go back and look. And I think there's a billion of these little nuggets lying around. We've identified some of them when we start to question it. We start to come up with a new hypothesis based on that questioning. But there's probably a lot of golden nuggets that laying around in the history we have yet to uncover. So
yeah, resonance is quantized as well, and it's not magical, mystical,
Yeah.
spooky weirdness. Like I can go in there right now and play a note on my guitar to make my snare drum on the other side of the room vibrate.
Yep.
I can also play an octave of that note and do the same thing. And there's different harmonic structures I can get, and it has to just do with the tightness, the tension, and the drum, the dimensions of it. So yeah, if your ultimate readout for electricity is the atom changing its harmonic states, well, it doesn't have to be magic particle stuff to have discrete changes in the vibrational states of an object. This is pretty well played out in the ordinary macro scale world.
I also want to add that there's something really fascinating about J.J. Thomson's story, because he was really preoccupied with the fact that when you read his papers from maybe like 1897 to 1905 or so right around the cathode ray experiments where he's getting really popular, he's basically like, I have demonstrated unequivocally that these cannot be etheric rays. I have demonstrated that they are electrons. And so he shows some supporting evidence for why it's the case. And basically, his evidence is the fact that he can deflect it with magnets, but etheric rays can't be deflected with magnets, because they hadn't shown that light outside of a medium could be moved or changed with magnets. Like Faraday had shown that you can change the polarization of light as it passed through leaded glass or like, I think maybe water or oil, but you couldn't take a magnet and deflect light. And so he's like, if I can deflect this ray, it cannot be a ray of ether, because the ether is not deflectable with magnets, but I can deflect it. Ergo, it cannot be ether.
But they had a more limited concept of the ether back then. They thought the ether was only electromagnetic. It wasn't on their radar yet that matter might be a wave of the ether.
Exactly. And so, but Thomson at some point, and so what's really fascinating is that you have this period of time where Thomson is writing this stuff about the cathode rays being little negative electron particles. And then he kind of disappears from the record. He gets a Nobel Prize for this stuff. His work is almost unavailable on the internet. And I found a paper of his from like, he died way late. He died like almost in the 40s. And I found a paper of his from the late 30s where he's actually like, what the fuck is mass? Like, where is this stuff coming from? Like, what gives the electrons their mass? And he's like,